So titration. This is a chemical method to figure out how much of an unknown solution you have. So let's say I give you an unknown acid. I don't know what strength it is. It's hydrochloric acid, but I have no idea what its molarity is. But I give you sodium hydroxide of a known concentration. Then you know it's a 1-to-1 reaction. 1 NaOH combines with 1 HCl. And so by adding a known amount of sodium hydroxide and exactly neutralizing it, you can mathematically tell how much hydrochloric acid was in there in the first place, divided by the volume, and you get the initial concentration. So in a titration, you add a known amount of a known concentration of something to figure out an unknown concentration of something. And so acid-base titrations are pretty simple. This pink color is coming from phenolphthalein. And it's clear in acidic solutions, but it's pink in basic solutions. And right after 7, that's when it turns pink. And so pretty much it's a good indicator of neutralization. Sometimes instructors will do the demonstration where you have hydrochloric acid, sodium hydroxide, and phenolphthalein. Then you titrate until it's exactly neutral and the person drinks it. That's a terrible idea. Don't ever do that. Phenolphthalein is also used medically to induce pooping. And so like it's used for constipation. If you look at the ingredients, you'll see phenolphthalein is a key ingredient in a lot of those medicines because it will make you have to go to the bathroom. So you should never consume that unless you need some help to go to the bathroom, in which case you should buy proper medicine from the store. But that is just a warning.
You'd find out real quick that whatever you drank was not good.
Yes, you would. Yes, you would. So indicators are chemicals that change colors at certain endpoints. And they're used all the time in chemistry and biology, like microbiology uses them in, for like mannitol salt agar. You have a phenol red in there because if something becomes acidic, it'll turn yellow. And then you can tell the difference between Staph aureus and Staph epidermidis based on whether it turned yellow or didn't turn yellow. And so they're useful because they can visually tell you exactly when you get to neutrality. You could also use a pH meter. It's a probe you put in, and then there's a readout of what your pH is. You could watch it that way too. It's just useful to have a visual indicator. A burette is a glass instrument that measures how much of something you deliver. So its number system is opposite. When it's full, it reads 0. And then as the liquid goes down, it reads higher numbers, because what it's measuring is how much you've delivered to the other solution, not how much is in the burette. So titrations. If 22.59 milliliters of a 0.1096 molar hydrochloric acid solution is used to titrate 25 milliliters of sodium hydroxide, what is the molarity of the base? First, put the reaction down, and it is 1-to-1. So that's good. With the stoichiometry, 1-to-1. And now we'll convert milliliters to liters times 0.1096 moles per liter, and that will tell me, or they just put 1,000 milliliters here, but both steps work. This will tell me how many moles of hydrochloric acid I delivered. And it's a 1-to-1 ratio, so for every HCl I put in, that neutralized 1 NaOH. So this tells me how many moles of NaOH I reacted and neutralized. I take that divided by my initial volume of 25 milliliters, which is 0.025 liters. And my initial solution was 0.09903 molar sodium hydroxide. What is the molarity of a sodium hydroxide solution if 21.93 milliliters of base is required to titrate 0.243 grams of oxalic acid? The formula is important here because that's actually a diacid, dicarboxylic acid. Oxalic acid is found in large amounts in the leaves of rhubarb, which is why you cannot eat the leaves of rhubarb, only the stalk. And oxalate is the anion of a lot of kidney stones, so you really don't want to consume that. But here you have 2 acidic protons. There's 2 carboxylic acids instead of 1, so it's a 2-to-1 ratio. You will need 2 NaOHs for every 1 oxalic acid because of that 2-to-1 ratio. So again, we put down our formula, but now we remember it's 2-to-1. And that's the key difference in this one. So I have my grams of oxalic acid. I convert to moles of oxalic acid. And then I remember I need 2 moles of sodium hydroxide to react with each mole of oxalic acid. So this is how many moles of sodium hydroxide I'll need. And they gave me the volume up here. This has to be in 21.93 milliliters, which divided by 1,000 to get 0.02193 liters. And we get an initial molarity of 0.246 molar sodium hydroxide. All right, let's take a 10-minute break.